Now we go to the fourth problem in our chapter. We're going to do pulling a mass up an incline. Now we did this before without friction. Now we're going to use a friction. Okay, so here we have the incline. Have a mass here going up to a pulley. And let's call this one big M and call this one little m, where the big M is going to win out, and we're going to be coming down here, pulling this little one up, and then you're going to tell me as part of the question to tell me what the conditions are with the masses, just how big M has to be to pull this off. And here the coefficient of kinetic friction is there. Okay, so that's the sketch. Now we go to the free body diagram. There's going to be two of them. Positive is going to be down, so going up is positive. So here, for mass 1, I have mg going down. There's my angle theta. I remember quickly, if I collapse this, this collapses and get the angle right. And then here is normal. And then here is tension going up and the rope pulling up. And then there's the frictional force pulling back. Doesn't hurt to emphasize that the plus direction is going up. And then here, the plus direction will be the one going down to be consistent. This is big mg going down and t going up. Now we're ready for Newton's laws. So this one here will be t going up minus f going back minus the mg sine of theta going down. And that's going to be little ma. This one's going to be big mg going down minus t is big ma. And then for the normal, we'll have the normal minus the mg cosine of theta equal to 0. And then we'll have the auxiliary equation. The frictional force is the kinetic coefficient times n. All right, using the solution, my method, I like to use the bottom, go bottom up. So I go with these two to get me that the friction is mu k mg cosine of theta, because n is mg cosine of theta, and then plug it in to that equation, you get this. Then if you look at these two, you can substitute in for the f. So you then get t minus mu k mg cosine of theta minus mg sine of theta equals little ma. And then I take these two equations, just like we did in the previous problem in this chapter, this kind of logic. We're going to use Newton's action and reaction to get rid of those tensions that appear opposite signs. And then we'll have here the big mg minus, and here, you know, I could see a factoring. Now let me go ahead and factor out the mg. So I'll have here mu k cosine of theta plus sine of theta, and out comes the mg, and that's going to be equal to, on the right side, the sum of the masses times a. So I'm almost finished now. So the acceleration is going to be, now I notice that I can pull g out, so I'm going to do that, have the big M first, and then we're going to subtract the little m times, and my preference here is to write the sine first, the sine of theta plus mu k cosine of theta, like that. And that's going to be over the sum. And then don't forget that we did have the g that we pulled out. So this is the answer for the acceleration right in here. This is it. So the answer to the question, like what are the conditions on the masses to get the big M to pull the little m up, to get the acceleration to be positive, you need to have this mass has to be greater than this combination here. So if that condition is met, then everything's going to work fine. If not, we're in trouble, because if the other mass is a lot bigger, it's going to go the other way. I've already picked the friction the wrong way then. I'll have to go back and redo the problem, but this is good for this arrangement. So now it'd be nice to find that tension. So the T, the tension, you go to a simple equation that looks a little intimidating here. This looks, the simplest one looks like this one. This one here looks the simplest equation. So the T, if I bring the T on the right side and subtract the MA, I have mg minus MA. This is the simplest way to go. T on this side is then mg minus the MA. And then what you do is you take this acceleration and you plug it in there, and then you have to do the math. All right. Okay, here we go. So this is going to be equal to big mg minus m times all this stuff, which is big M. I'm just going to copy, just copying this stuff in here. Sine of theta plus mu k cosine of theta. And that's going to be over the sum of the masses. And that's going to be g. Now notice that there is a big mg in both cases. So let's go ahead and get that big mg out of there and have 1 minus the numerator and the denominator. And now what I would like to do here is put in for 1 the sum of the masses over the sum of the masses, so I have a common denominator, and now I can like figure it out. And I'll figure it out over here. T is, I got the big mg on the outside, and then I'm going to have here over the common denominator the sum of the masses, like this. I'm going to have the sum of the masses, and then I'm going to subtract all this stuff. Maybe go like this to just have the different brackets. Now here you can see that the big M is going to cancel, and then the little m is going to factor out, and I'm going to have here the product of the masses, big M times a little m, over the sum. I'll save the G for the far right. And then here I'm going to have the little m is going to be 1 since I pulled the little m out. And then here, the 2 minus signs here will cancel and get a plus sign. And this will be plus sine of theta. Remember, the little m has been pulled out. Plus mu k cosine of theta. And here, a g is at the end, like this. So that should be it. That should be the answer. Let's check the dimensions on both of these. Here, masses cancel, you get g, acceleration. Here you have an extra mass up there, it's going to survive, and you have a G, so it's mg. That's going to be the force. Now, do you remember when we had the two masses over a pulley? We can get this situation if we were to let this angle, or let's say let this distance get shorter and shorter. So you have a case like this. You say like that. So that means the angles get bigger and bigger, and then like even, or like, you know, like that, the angle is going to be 90, and it should then be this kind of a problem. And here's the answers that we got. Let's see if we get these answers. Now you got to be careful here. This one is the big M, and this one is the little m in our problem. So that means this is big M minus little m to adapt these, and this is going to be the sum of the masses. I'll put the big one first, doesn't matter there. And then here T is 2 big M little m over big M little m G. Okay, so this is what we have with our notation in this problem. So let's see what happens if this should be the case where we go 90. Well, if we go 90, then the sine of 90 is 1 and the cosine is 0. So in other words, we get big M minus little m. Like we got it, like it works. All right, isn't that cool? And then if we go to this one, if the angle is 90, this becomes 1, and this becomes 0. Cosine is 90 is 0. That's 1 plus 1. That's 2. That's two of these. That's it. Works. Isn't that nice? Very, very nice.